So when you get your shellcode to execute for this exercise, this is probably the hardest exercise in the class. I want you to throw up your hands and say, compliment it on close. And unless you say that, I won't acknowledge you. I'll just say, nope, no one's got it yet, I guess. And the one nice thing is that even though this is a dynamic memory, the allocations are predictable. So if you do an allocation of 128 bytes, something like that, and put your shellcode in that, the address for that heap chunk will pretty much always be the same because the heap allocator is deterministic and the memory addresses it chooses, basically. And that's true with many memory allocators. And that fact is widely abused by many like browser exploits and stuff like that, that these memory allocators are just deterministic and you can guess where the memory is located or where it's going to be located when you allocate things. And when you can't guess, you do a heap spray, fill up the whole contents of the heap with stuff. So that way you don't have to guess because everything contains your shellcode.
Corey?
Yeah.
Dumb question. You said that the buffer has to be large enough to contain our shellcode.
Yeah.
But aren't we just pointing the global object able to execute our shellcode, which exists somewhere else?
You should copy your shellcode onto the heap. Okay. I mean, you could technically just put your shellcode on the command line, and then it would be on some stack address, which is where your command line arguments end up.
Oh, that's what we did last time.
Yes, but I would suggest that you do like a string copy from the command line to the buffer. It will be easier if you just put your shellcode in that heap chunk because that address will be more reliable than the addresses that exist.
Oh, that's right.
Okay.
And that's basically just because you know that the first heap chunk will always be allocated to the address 80 or 0804. 8010 or something like that. It's deterministic, it's always going to be that address, whereas on the command line, the addresses are kind of shifted around a little bit, and that's kind of frustrating to debug. I would probably recommend as well getting rid of like dump heap commands and stuff in your code once you know that you have the crash that you want to have, just because the dump heap thing might end up, you don't want your program to crash in dump heap, you want it to crash in the allocate. So if I was exploiting this, I mean the alloc user file I would use would be, if I can recreate this from memory. Yeah, I would just use something like this.
Were we supposed to use is the idea that we're going to use the rbright code to manipulate the global offset?
No, because the rbright code will only manipulate its own global offset table.
Okay, so we need to add some C code that will do that.
Yeah, I mean you will overwrite you will modify the global offset table because that's what you'll put the address of the global offset table in that next pointer field in the control block.
I got that, but in order to, okay.
So just remember that the global offset table is a per process thing. Each time you restart an application, I mean, you can change the global offset table for rbright, and in a second the process is done executing, the global offset table is the same again, because it gets recreated each time you run the process, okay? And it's a per process thing. It's not like you can just change the global offset table for one program, and it should change system-wide for everything else from there on. Each process has its own global offset table, and each time it runs, its global offset table gets restored and fixed. So you'll be changing the global offset table for the memory allocator as it is running. So here's a little push in the right direction. You know you're corrupting a control block. You know that next pointer, this next free chunk should be set equal to like the global offset table minus OXC or whatever, right? Because the offset thing is the net result of that offset calculation to be 0. you know that the previous free should be set equal to shellcode. Yeah, making sure I'm not getting the order wrong for these. It might actually be the other way around. Let me
do it the other way, but use a different offset. You have to use -8.
Yeah, right. So I'll verify that in a second. So yeah, global offset table shellcode. What about these? What are you guys ever running these with? Available in size.
Available 1 and size 128.
I just did
Depending on what you're using.
Like 01, 01, and let's just keep the nulls away.
Yeah, because you can't just rewrite the 1, because then you'll have null characters on the payload, and the string copy will stop when it hits that null character. You also can't make this too big. You can't make size equal to OXFFFFFFF. Why is that? Because then it'll be treated as a negative number, is the way that sign numbers work. So so available has to be non-zero, all right? That's pretty easy to do. It has to be non-zero, not contain null characters. Size has to be greater than 128 or whatever, you know. It has to be big enough to satisfy that allocation request, but it can't be too big, otherwise it'll be treated as a negative number. So it can't be bigger than like, is it 7 FFFFF, I think it is. So what I would do is I would set available equal to OX11111111, and then size equal to OX11111, which is a huge number, but the allocator will still use it and it's not treated as negative. You could use 010111, that's fine too. And then let's look at these again by looking at the allocator code. Okay. Trying to throw you guys a little bit of a curveball at you, just because I was telling you the wrong order. I don't think it would matter, but just to keep everyone on the same page, this is how I want you to do it. So I had told you to set next free equal to the global offset table, right? And then previous free equal to your shellcode. Let me think for a second. So I told you next free global offset. Let's see. No, you know what? You can try it that way. Go for it. I was about to say that instead I want you to set the previous free equal to the global offset table and next free equal to your shellcode instead of the other way around. You control both those pointers. Since this first line here is saying previous free equals next free, it would be global offset table equals your shellcode. And if you had it that way, if you come down here, that would mean shellcode equals global offset table. But that's going to happen either way, actually. So what's going to happen is that sort of nasty thing I told you was going to appear, was that in the middle of your payload, you're going to get some random bytes in there. And it's because of one of these other writes. So if you check previous free, global offset table, next free equals your shellcode. And down here, the address of where your shellcode is located, plus some offset, equals the global offset table. So the bytes associated with the global offset table. So that means your shellcode would have 0804 something, 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 something right in the middle of it. So what you're going to do instead, and that should happen if you choose either one, if instead you make previous, the other way around, that issue is still going to come back up. So what you're going to do is, instead of it pointing directly at your shellcode, instead of pointing the global offset table directly at your shellcode, you're going to point it at the middle of your no-op sled. And then this line right here will write some junk into the middle of your no-op sled. And then you'll have to figure out a way to jump around that. So the point is, you can make previous free or next free the shellcode or the global offset table. Either one should work because you're setting one equal to the other and the other equal to that. A equals B, B equals A kind of thing. So either one should work. You'll just have to adjust your offsets like into the structure accordingly. So yeah, keep on fighting. How's everyone's morale feeling? Want to do a morale check? People feel like they want to jump off a cliff at this point? Okay. The last half of the day we'll have sort of a change of pace where I talk about some more high-level stuff like finding bugs, exploit mitigation technologies. So if you're, you know, not enjoying the more technical intensive labs, there will be a break from that for a while at least. But then we'll finish strong with one last technical lab where we bypass the next speech stack.
So Corey, I'm still just trying to understand the kind of the theory a little bit. I understand that we can overwrite the control blocks, and we can do it cleverly to set the detour address with previous free chunk to equal that, and that next free chunk we could set that to our shellcode address. But we still need something in the code to actually execute and go to the DITR's address, right? So and how is this allocation deallocation it's not really executing code that's going to call this, is it?
Yeah, it is, but it's confusing because it's implicitly doing it. So the destructor will be called when the program goes to exit. So whenever the program is going to exit, then the program will execute your shellcode since you overwrite the destructor with the address of your shellcode. Or if you overwrite the global offset table with the address of your shellcode, the next time it calls like printf, or puts, or whichever one you overwrote,
I got that, and I
shellcode.
understand how we did those. I guess what I'm not seeing is how overwriting our control block impacts either the GOTS or the DITRs. And if we couldn't, we're assuming. I guess we're assuming we didn't get access to the GOTS or DITRs directly like we did before. We're trying to take advantage of the allocation program to do that.
Yes. Exactly. Yes, and so so we overwrite those pointers in the control block. You got that. And then when this code right here that I'm showing on the screen is in the allocator is executed, we control like the previous free chunk pointer.
Yep.
And the next free chunk pointer. And essentially what this line of code is doing is saying previous free chunk equals next free chunk. So in our case, global offset table equals
and I got that. What I guess I don't understand is the allocator is just going to look at these values to decide where it puts the new chunk, right? I mean, it's not, if it sees this value, the worst thing it's going to it's not necessarily going to jump there and call what's there. It's just going to say, okay, that's where I'm going to build my new, you know.
Right, and so that's right. We're not gaining control of the instruction pointer directly or right after we perform this. We're only corrupting some memory that will later be used to control the VIP. And so eventually when we use this to overwrite the global offset table or the destructor, eventually later on in the program's execution, we'll grab control of EIP when something like printf is called and the global offset table is referenced or something like that.
Okay, so we're just using this as a convenient place to store our shellcode, I guess. And okay.
And we're also abusing it to actually change the global offset table or the destructor.
Okay. But okay.
So normally you can't just change a program's global offset table when it's running.
That's right.
Normally that is not possible, but we are using the overflow and this line of code in the memory allocator to change the global offset table, which we normally cannot do. And then because we can change the global offset table, eventually that will allow us to gain control of the instruction.
Okay, so like we've established the address, it looks like, of the global offset, or actually with this, like we're doing it with ditters. So we're telling it where that's located in memory, and we're putting a pointer to that in the control block, right? So I guess where in the code, in the allocating code, is it going to that and going to that address and making changes in the ditters part of? Yeah.
So first off, I would recommend that you use the global offset.
Okay, we'll use global offset. Okay.
Both should work, but the destructor might actually be a little bit more complicated. But so let's assume that you've you do the buffer overflow and you've corrupted the control block, right? You control the next free and the previous free pointers.
That's right. We got those.
In the control block. Then, when this line of code executes, alloc 128, it will eventually call. Yeah, and that's kind of fine. Just trying to scroll down to the code for alloc. So eventually, this will be executed. It's going to find that chunk of memory to give back to the user, and it's going to unlink it from the free list and call this function right here, unlink chunk. Okay. And it's unlinking the chunk whose control block we have corrupted. So then we'll execute this group of code right here. And essentially what this code does is set previous free chunk, the address of whatever points to whatever. Interpret previous free chunk as a pointer and set whatever it's pointing at equal to next free chunk. So in this case, it will set global table for like printf or something equal to address of our shellcode.
Oh, okay. So we're not really okay. So we're taking advantage of this this part of alloc, not really to assign new memory, I guess, but we just happen to overwrite. Okay.
Yeah, we're taking advantage of it to arbitrarily change 4 bytes of memory in the process address space. And then once this happens, even though alloc user.c doesn't call printf, the memory allocator is calling printf a lot. Like whenever it does one of these alloc logs, it's calling printf. So the next time one of those happens, then our shellcode will be executed because we've overridden that global offset table with the address of our shellcode. Has anyone got it yet? I don't know.
What is it I'm supposed to say again?
Papa Legba, hear my call.
Papa Legba, you're my call.
Yeah, so you got your shell executed?
Yep.
Okay, cool. So, did you have to do the relative jump to get past the bad bytes?
Yes.
Okay. Because actually sometimes the bytes will assemble into crappy x86 bytes, but not any bytes that will crash the process. So it'll just be like add AX 3000, you know, floating point divide, and some other weird x86 instructions, and the processor will just say, okay, whatever, and just keep on trucking. And other times it'll do something bad, like divide by 0, try to dereference a bad address, and it will crash. So it's actually good that you had to do that and then do a relative jump past it. So probably what we're going to do, guys, is keep doing this up until lunch, which we'll say is at noon, and then just take a 1-hour lunch. So if you've already gotten it, like Josh, you can feel free to go elsewhere and come back at 1 o'clock, or if you want, I'm sure I can find some more fun things for you to try to dabble in.
Are there any heap allocators, not your toy one, but real ones, that do anything at that metadata level to try to check, like a CRC checksum or something?
Yeah, they've started doing that. So like a lot of them have safe unlinking now is what they call, where they will, and this has only happened pretty recently, they'll sanity check the previous index pointers before they try to dereference them and use them. However, what you will find, which is kind of weird, is that a lot of applications out there implement their own allocator, like on top of the normal system allocator. For whatever reason, it's like every programmer wants to write its own memory allocator. And if they're doing their own custom allocator, this kind of stuff is still on the table, and there's still other allocators that are vulnerable to this type of thing. And in general, with heap overflows, the techniques are always kind of changing and evolving a lot more than stack overflows. So this is sort of a prototypical technique that's been around for a while and it's starting to be mitigated. But understanding how the heap works and being able to draw heap diagrams and understanding what your corruption is doing to the heap, eventually, if you understand that really well, you can still find some kind of crazy way to get arbitrary 4-byte numbers. But yeah, it's always changing because the allocators are always changing and becoming more optimized or more secure or this or that. And then, some programmer at another company, they'll write their own memory allocator framework on top of the system one. And the system one does safe and sanity checks, but the custom one does not. And so you can use the custom one and stuff like that. So
Like Adobe.
I wouldn't name names, but you'd be surprised how many companies do that. It's really kind of surprising. It's one of those things like crypto where you really shouldn't try to do it yourself because it's really hard to get right, but everyone tries to do it anyway for whatever reason. And I can only guess it's because the programmer's like, well, you know what? I know my program better than the Windows programmers do since I programmed it. So I can program the allocator to be more efficient for my type of program since I know that my program is only going to use 128-byte chunks. So I can optimize it for that size of allocator or something like that. Kind of open up a worms and try to implement something like that yourself. That's not nice. And then with something like use after free, you're not even corrupting any chunk meta information. You're just abusing the patterns in the memory allocator to gain control of the IP, basically. And I'll try to talk about that a little bit more for lunch as well. Then you have memory allocators like the OpenBSD memory allocator, or ones that will be super secure. And they store basically all this meta information out of band with the actual heap. So it's just all stored off to the side in its own kind of memory pool. And that way, buffer overflow won't corrupt that meta information that the heap allocator is using. But there's a cost with that, and that is more wasteful of memory space, since you're having to kind of keep this whole other pool of memory just for the meta information instead of storing it in line. But when you have an operating system like OpenBSD, you're willing to make that trade-off of security for performance versus security. So,
Yeah.
what you're doing, and it doesn't matter if you do it either way, so you're doing like previous chunk equals global offset table, or something like that, and then next free chunk equals shellcode. But then look at this next line. This basically does shellcode equals global offset table. So in your NOP sled, it's writing in the bytes associated with the address of that global offset table, and it's trying to interpret those as x86 instructions. And it's, some people got lucky, and those x86 instructions turned into something that would not crash the process, just turned into some arithmetic instructions or something. In your case, either they were bad instructions that the processor couldn't even handle, or it was trying to dereference a memory address which is bad or something like that, and it's just crashing the process before it even gets to your shellcode.
Okay, but why do they get inserted at those places in memory? Is that memory was dedicated for that allocated code, right?
So, global offset table equals your shellcode, but then your shellcode plus previous free. So your shellcode address, whatever address you put up here for your shellcode, which is probably in the middle of your no-op sled, right? Some address in the middle of your no-op sled. That address plus
So it's that
C.
second line that's adding those. Okay.
Yes, plus, so that address plus C, so you can't just jump around it. Whatever address you put here, that address plus C is going to get those bad bytes.
Okay, so I could try to eliminate that by manipulating that second line and making sure it points to something valid or.
But you can't get around it. You just have to deal with it because no matter what you put, it's like A equals B, B equals A. There's nothing you can do. The way you get around that is you just have to hack in that jump into your no-op sled so that you hit the jump and jump over all the paths.
So you actually edited assembler?
You put it in your payload in the no-ops.
So you just actually put whatever the hexadecimal bytecode for jump is?
Yeah, so you have to figure out what the hexadecimal bytecode is for jump, some 1 byte offset, and then figure out how many bytes you need to jump.
Thanks.
So we were fumbling around, or I was fumbling around for a while trying to get that to work in the assembly source.
Yeah.
And never did, so.
So
Then I heard you say something, just hard code it, so went and did that. But I'm not sure why it wasn't working. According to, I was looking at the.
Oh, so you actually trying to put it in your shellcode source?
Yeah, in the manual it said you can do jump, all caps, short, and then an immediate value less than 128.
Yeah, but if you just put it in your shellcode, then you're pointing the global offset table at your no-op sled, right?
Yes.
Basically, whatever you set the global offset table to, that address plus C plus C of x to the offset gets set to those bad bytes.
Right.
Bad bytes. So you have to figure out where the bad bytes are ending up, and then just hack in that jump right before it.
Yep.
And if you can't adjust, you can't say, well, I'm just going to move it a little bit forward to get past the bad bytes, because no matter where you move it, wherever you move it to, plus some offset is going to get bad bytes.
Yeah, I mean, 8 bytes and 12 bytes into it are both going to get.
Yes. So you want to just point it in the middle of your no-op sled, because it's okay if your no-ops get jacked up, because they don't have to execute for your shell. And but if you were to point this right at your shell code, it would jack up the middle of your shell code, and there's nothing you can do to recover from that, because your shell code would be bad. So you point it to the middle of your no-ops, because your no-ops can get clobbered, doesn't matter, and then just put in that, in your no-ops, in your payload file, just change it, 2 of those OX90s to like shell 30 bytes or something like that.
And then what I tried to do before that, that's what I have now. What I tried to do before that was modifying the assembly source and putting in a series of no-ops and a jump before it.
You could do
To a
that.
label after it. I thought, but for some reason I couldn't get it to.
It would compile.
No, I kept saying that the jump was out of range or something.
Were you trying to jump to a label or trying to jump like a number of
I
bytes?
tried both.
And neither of them worked?
No, I didn't want to.
Might have been you had too many no-ops, and it was not liking to jump short for the distance you were trying to jump.
Maybe. I don't know. Anyway,
But yeah, that's, I haven't tried putting in the actual assembly file yet, but that should be valid. So yeah, I'm not sure why you would do that.
okay.
But yeah, the correct thing is just to figure out what the opcode is for the jump short. I think it was like EB or E8 or something like that. And then like 30 bytes.
Yeah, it's EB and then
Yeah, one byte offset.
You talking this?
one thing, I don't know if anybody else stumbled on this, but I did for a little bit. There's a build.sh script in the
Yeah.
alloc user directory,
Yeah.
but it doesn't have the -G option for GCC, so it didn't have debug options.
There you go.
I was in the debugger, which I don't know GDB that well, and I was stumbling around, like, why isn't it printing anything? Why can't I list anything? That's why.
Yeah, so it might help you out a little bit if you had a -G in the build script. So you know what I'm saying.
To figure out like the byte code for jump, I found out that is the best way to just run a program and reverse engineer.
So this is what I would do.
I'm trying to have a jump to an address and there's no consistency. What's the short?
That means just jump 1 byte worth. You know, it makes it like you can only jump like 255 bytes ahead.
Ah,
Otherwise, you'll get a bunch of null bytes.
okay.
And ooh,
What was that command to display that?
OBJ dump.
Yeah.
Just the
With what argument? -D or?
dash lower D.
I did that like a.
Then you can see you can just do EB, some number of bytes, and that'll jump me 1, 2, 3, 4 bytes ahead. So what I'll do is I'll start working through this on my own, and you guys can see how I'm doing it in case you're stuck. Want to get some tips about how I go about through the process. So hopefully I won't screw this up too bad. Okay. So, just to recap, I know that I'm overflowing buff 1 into a free chunk buff 2. I'll have to write 128 bytes, and then I'll be overflowing the second chunk's control block data. So, go ahead and start building my payload here, get some shellcode I want to use. There's a shellcode I'm going to use. Need to figure out how big it is, that way I can get all my sizes right. 45 bytes. So, At this point, I've got 128 bytes. This will completely consume my my first chunk. After this, I've reached the point of no return. I'll be overriding the control block for the that second chunk that is free. So let's see what I want to change these to. All right, so after I've overridden that first 128 bytes, I need to figure out what I'm going to set that control block to. So I'm just going to draw a little bit of diagram here. So available, this has to be not 0. I'm just going to make it equal to OX11111111. Size has to be greater than 128, but not so big that it's negative. So I'm just going to make that, I'll actually make it 2. That way I can just check my alignment, make sure everything's ending up the way it's supposed to. Next free, I'll set this equal to global offset table. You guys were using next free as your global offset table, right? Or were you using previous free? Either one should work.
Next.
Next, okay, so you're using next global offset table? Okay, so I'll set this equal to some global offset table. Which was the one that was causing crashes? Was it printf or puts?
Printf.
Printf is causing crashes? Okay. Okay.
Works fine.
Yeah.
Just depends.
Yeah.
Oh, really? Who got a crash and had to do the jump 8 thing? And which did you use?
Printf.
Printf. Okay, we'll use printf and see what happens then. So got print f minus what do I need to subtract by in this case? Is it c? OXC. OXC, since it's the next free, previous free, 048C. Previous free equals obsolete. Okay, so let's get to work on doing this. Alrighty, so let's add this into our payload. There we go. That represents having overridden the size and the available field for that chunk we're corrupting. Next comes the next free pointer. Need to figure out what's the address there. Kind of looks like C58. So that is the printf global offset table minus 12 or OXC. Okay, and I'm not really sure where my shellcode is at this point, so I'm just going to put in a placeholder value and go find it. So dead beef. Okay, so there's my payload file. The last one is the dummy placeholder value now until I know what the address of my shellcode is. So let's fire up the program with the payload. Set a breakpoint for after string copy because I know that this is where my payload is entering into the heap. That way I can scan the heap for where my shellcode and my no-ops are located. Okay. Now, since I'm just going to cheat a little bit and look at my allocator output to kind of know where the address is associated with the heap are. So your addresses are probably the same, 804A 000. My knob should be somewhere in that vicinity. So let's go take a look. So, yep. Looks like this address will suit me just fine. 804A030. I'm avoiding 20 since 20 comes out as a space and ASCII code can cause problems for my payload. 30 should be a perfectly safe character. All of these characters look pretty safe. A030, 04, 08, all good. So I'll use this as what I set the global offset table to. Was it
A030?
Right?
A03, yeah.
Okay, so my payload should be ready. Let's see what happens. Hopefully I'll get a crash actually, so I can try to debug that. Just in case, I'll go ahead and set myself up to receive core dumps from any processes that crash. Uh-oh. Okay, so what went wrong? We didn't even get a crash, so let's try to figure out what happened.
Of course, do you have to sit there and do the arg bytes or alter the GOT?
No.
You do not, okay, I thought you did.
No. The arg write was just demonstrating that if you arbitrarily change 4 bytes of memory, then in a process, then you can gain control of EIP. But this is on like a per process basis. Each time you start up a process, the global offset table is restored. So you can use arg byte to change the global offset table for arg write, which is what it's doing, but that doesn't affect any other process that's going to happen in the future, arg write or not.
Sure.
Okay. So let's see what happened. 128 bytes. All right, I'm going to get a piece of paper here to write down some of these addresses for me to check out in the debugger so I can see what I did wrong. Can anyone spot what I did wrong at this point? Because I cannot. I do not know. So, let's double check all this. I'm guessing maybe I screwed up the address of the printf or something like that. So what I'm trying to overwrite, my global offset table entry is 0x0804 9C58, and that address is this next previous. Should be 804 49C4C. Okay. What I'll do now is I want to verify that the global offset table is getting overwritten with the values that I think they are. So I'm going to set a breakpoint for unlinked chunk towards the end here where I know that the override should have happened. Because that's when we do the A equals B, B equals A kind of thing. So I'll set one for that's me. It did not even try to take our off of the. I think my size might be screwed up here. Okay. Start from the beginning. How about that? All right, 128 bytes. That's correct. All right, just so we can try to get a crash, just to start from the beginning here, since something is not happening as I suspect, which is often the case in the wonderful world of exploits. I'll just add some placeholder values here to the end.
You said, should that be 24 bytes of the 1-1?
I just decided to set,
Oh, you
yeah,
along
the
the ones
available
in.
size
Got
of
it.
the same. Okay, it looks like I got my size screwed up on the other one because these sizes are already looking different.
It looks like you're stepping on the SH part of, oh no, it's just going, never mind.
So this should crash. It's not. That's me. What is going on? Ah, very stupid. I have not compiled the allocuser.c file in a long time. Okay, there we go. Now, Corey just made a horrendous rookie mistake, and he was working on that exploit, and the source code he was looking at was not even recent. So, and now we should see some things happen. There we go. All right. So let's see what happened with the crash. Okay, so as expected, I just use those placeholder values, and I get a crash in unlinked chunk, mainly because previous free chunk and next free chunk have been corrupted, so it's trying to set like A equals to B, because that's what I set those values to be. But I did forget to get the address of my shell code. So let's go and find where that was. What was the address of the shell code that someone used, by the way? What are those heap addresses? Was it 804A? Is that right? 4A? 000? Yeah, there it is.
Yeah.
Okay. So shell code address I'm going to use is 804A030. Is this one right here. So let's go and hex edit my payload and put those values in. Let's see here. This one is going to be the address of the global offset table minus OXC. So 4C C408. Yep. And then the address of my shell code, which I just found, 30A004. Okay. Now, let's see, what just happened? Looks like my shell code was not executed, and I'm not really sure why at this point. So I just kind of want to see what's going on in the program. So I just set a breakpoint for the unlinked chunk thing after the overwrite should have happened. And I want to check out what my global offset table looks like so I can verify, number one, that I'm actually overwriting the global offset table, and two, that I'm overwriting it with the correct values, the value of the address of my shell code. So, say X OX8049C58. That's just the real address of the global offset table, not minus OXC or anything like that. And yeah, there we go. So my shell code is ending up in the global offset table, so that is good. We see that this first entry in the global offset table points to a 0804A030. Let's see if my shell code has actually ended up there. Okay, and it has. Now let's see if that even gets executed. So what we can do is set a breakpoint for OX804A. I'll just put it somewhere in the middle there. C for continue. And it never gets executed. So I'm suspecting that in my case, printf was not getting executed, maybe because I didn't have a dump heap or something in there. So instead, I'm going to try to replace that global offset table with puts instead of printf or something like that. So let's go ahead and calculate the global offset table for puts. Okay, let's see what happened. You guys used printf and it actually did work, right? Yeah, all right, so I once again made another dumb mistake, and I got the global offset table value before I recompiled, so that I recompiled and the global offset table has changed. So I'll just overwriting, it looks like I was actually overwriting the G start, which isn't going to do any good. So I'll change that to 8049C78. and do the subtraction on that. Shellcode address should not have changed though, since these heap allocations are deterministic, so I'll just go in and change the address of that global offset table entry. 08049C6C. There we go, all's off. Okay, good, this is what I wanted to see. So, my shellcode did execute. I probably hit those bad bytes, which is why I got that segmentation fault. But at least I'm not making any dumb mistakes like I have been the past 10 minutes. So it's time to go in and debug what's going on here, and what we'll see is probably that it's saying EIP is equal to some heap address, and if that heap address are some bad bytes, like you guys were seeing, maybe a jump or dereference to somewhere bad. So, look at the core file, there we go. Crash in the heap somewhere. Let's check out what's at those, that address. Okay, here it is. So this is probably what's crashing the code. You can see it's actually dereferencing, trying to dereference like EDI or DX or whatever this crazy instruction is in x86. And that's causing the crash. So what I need to do is put a short jump in here somewhere and jump ahead like 10 bytes or something like that. So I'm going to hack that into my payload and try to get lucky. So trying to eyeball where I should put the relative jump in my payload. I know that my payload starts at A010, just from prior experience, since that's the beginning of chunk 1. And this is at 030, so it looks like I'll have to go 20 hexadecimal, 32 bytes ahead in my no-op payload, and put the relative jump somewhere in there. And as you guys discovered, the opcodes for the relative jump is EB, 1 byte offset. So let's try to do that. Okay, so that's 24. Would that be enough? Put it guessing a little bit here. Yeah, okay. This is a kind of a stab in the dark by me because I'm just trying to guess where to correctly place the relative jump in my payload. I might actually be returning here, in which case I'd miss it, or maybe jump forward 10 is still not going to jump me past those bad bytes, but we're just going to try that one and see if it works or not. So we'll do this in the debugger just so we can see what's happening. Okay, so at this point, the global offset table should have been overwritten, and my shellcode should have bad bytes in it as well. So let's just look at those bad bytes to see if my jump is going to clear those and if we're even going to hit the jump. So if I recall correctly, I set my return address equal to A030. So just going to look in that ballpark. I'll do 20 just so we have some stuff leading up to it. Okay, so right at 30, I guessed very well. this is where the stuff was returning to. It looks like I'd be returning right to my jump, but let's see if I jumped far enough away to get past the bad bytes. As it is right now, we would jump to 4A042, so as long as this is beyond the bad bytes, I'll be all safe. And it looks like I should be safe, right? Because 42 is down here. So let's see and see what happens. Yay!
Say it.
Yeah, you made us say it.
How to let God.
Hear my call.
Okay, so did that process kind of make sense? That turned out to be better than I hoped it would be, since I obviously made a couple other mistakes before I got to this. Did the debugging process make sense a little bit for you guys? Mike?
Yeah, that's great.
That helped a little bit?
Yeah.
So we still have a couple people, or a few people really working on it. So I want to give you guys a little bit more time on that since it's an important lab. For you others that have already had success, what can I dream up for you? Okay, for you other guys, what's y'all working on this one? Frame point or override?